Okay, so it looks like recording has started. So thanks everyone for coming. So I think this week we have, I guess, another talk that has some AI flavors to it, which is porting SSProve-Lean 4. So SSProve is a library for formally verified cryptography in Rocq that Baz has been working on, I guess, for a couple of years now, at least, and which has also been used to verify some Rust codes and have actual kind of practical results beyond just proving things in Rocq. Baz is faculty at our house, has been doing every possible flavor of form verification, as far as I can tell, from homotopy type theory to, I think you have a paper on quantum something, to verified cryptography, to verified software, with obviously many PhD students. And yeah, I think more recently you've been working quite a lot on interoperability between proof assistants and bridging Lean and Rocq in particular, which I guess this is an example of, and I'll let you take it from there.
Thank you for the introduction. I haven't changed my background, but we'll leave it like this. So we've been one of the big problems in formal verification is interoperability, and we've been talking about this before, Alex, and we also talked about this at Hex. Now, I had some experience translating code bases from one proof assistant to the other. I tried to translate some things from Lean to Rocq, and played a bit with translating mini F2F. We just got a type abstract. Was it accepted where we explained it, where we laid this out. We could translate from standard Rocq to mass comp, so that works quite well. And the one issue is we've been working with the Hex tool chain, so that's to verify high assurance crypto written in Rust, and then this is connected to SSProve to do security, cryptographic security in the computational model. But Hex is moving to Lean, and there are other tools also in Lean. There's close collaboration with Anias, and there's not a good system for computational cryptography in Lean. So I thought I'll just try and see how much I can do translating it from Rocq to Lean, and this has actually been quite successful. So let me first refresh your memory on what cryptography does. So we have security games. It's a probabilistic experiment between a challenger and an adversary, and the adversary tries to figure out what's the what the challenger is hiding. So you have some secret randomness, and the adversary interacts with the challenger, and then the adversary needs to guess whether the output is A and B, and if that things stay secret, if the probability that you're in the random model or in a secret model, they're the same. So what you need for this is an advantage. So that's the probability that that the adversary guesses one in one game or guesses one in the other game. And what you hope is that the advantage of the adversary is small. And then what typically you do is you define some cryptographic protocol, and you reduce it to a well-known cryptographic assumption. And this is done in first in Certicrypt. I mean, this has long been done in the cryptographic community, and this was made more precise by Valera and Rockaway, and then implemented in Rocq first in Certicrypt, and then in the standalone tool EasyCrypt to do this game hopping style reasoning, and then it was re-implemented later in a slightly different way in FCF in Rocq, and in CryptHole in Isabelle. But let's get back to the game hopping. So you can do some dead code elimination, copy propagation. You can do reduction, showing that if you can break this protocol, then you can break a well-known hardness assumption, or something statistical. So the probability that a bad event happens is really small. And This is something like a birthday bound or switching lemma. In EasyCrypt, this would be the failure event lemma. And what we want to do is, again, formalize this reasoning in a proof assistant. This has been done a number of times before, and most primarily in EasyCrypt. So in EasyCrypt, you have this probabilistic relational Hoare logic, and then you reason about equivalences between programs. So M and N are modules, and then functions in this module, and then there's a precondition and a postcondition. So you would always be reasoning about two programs at the same time. So that's the R in relational here. Can you see my pointer, by the way? Maybe not. So,
yes.
oh, you can.
No, maybe not actually.
No.
I was just,
okay.
I think mine was on the screen.
There's no point in me pointing them. And the nice thing is that EasyCrypt, it's close to what the cryptographers write by themselves. It has a very mature tactic language, tactic library. It's all implemented in OCaml. It reduces to Y3, which then again reduces to external SMT solvers. So that part is unverified. So it's not foundational. And EasyCrypt has a number of embedded logics. So there's the probabilistic relational Hoare logic, there's the unary Hoare logic, and there's the p-Hoare probabilistic Hoare logic, and then there's the ambient logic. And the ambient logic has a tactic language that's very close to SSReflect from Rocq. Then there's FCF in Rocq. I don't think that's still maintained. So that does game-based proofs in Rocq, and this has been re-implemented or ported. I don't know what the precise relation. Maybe it's just an inspiration for the Lean library. So that's what's currently available in Lean. But FCF is nowhere as developed as EasyCrypt, for example, and it's also not. There are certainly limitations of what you can do there. So the core computation there is the free monad over oracle queries, and then you have substitution of oracles. This is built on a probability type, so probability mass functions, and then if you want to build in non-termination, then you allow the mass to be less than 1. So you apply the probability mass function to the option of alpha. This is also what's used. So this is what they got from, this is implicit in what the cryptographers are using. And this is something that's, so it's also used in EasyCrypt and in SSProve. This is some general overview. So EasyCrypt is not in a general purpose proof assistant. It has limited support for compositional bounds. So there's no categorical structure. That's also not available in FCF. EasyCrypt has deep and shallow embeddings. The FCF only has a deep embedding. And so what we have in SSProve is both the deep embedding and the shallow embedding. There's the coupling technique, which allows you to do probabilistic reasoning about two programs at the same time. And the states are, so the difference between FCF and EasyCrypt is that FCF is functional, so there's no actual state. So if you want to do a stateful project in FCF, you really need to pass it along. So that becomes somewhat awkward. In EasyCrypt, it's embedded. EasyCrypt is an imperative language, and we'll also have an imperative language here. So this is what we implemented in SSProve some time ago, a couple of years ago. Deep embedding. That's a very good question. Thanks for and thanks for asking questions during the presentation. A deep embedding means that you actually have a presentation of the syntax available in your proof assistant. Whereas a shallow embedding means that you have a shallow embedding of, say, a functional program. A functional programming language would reuse the functional programming language of Lean or Rocq for your functions. And this is very convenient for many applications, but for some applications you actually want to have full control over the syntax, and then you can do all kinds of analysis also on that. And it's also very convenient if you want to write tactics, because then you just have the program and you can do all kinds of manipulations. To some extent, if you have a very strong meta language, that somehow gives you more control over the shallow embedding, and that may also be a reason why actually using the shallow embedding, or whether the shallow embedding is actually more well behaved in Lean. So what we've been working on for quite some time is to work on SSProve in Rocq. And so this actually worked very well, but now we ported and we also changed some of the infrastructure to Lean 4. So again, the setup is the same. So we have sub-probability distributions, and one of the things I did was to actually make the categorical framework a bit more clear, although the categorical framework was already very much available in SSProve, but not so much in the definition of packages. So I'll get to that in a minute. So FCS is FCF and VCV, as we just saw, it doesn't have state. So here we want to be close to certicrypt and easycrypt. So we take the sub-probability mass functions and just weave the state monad through it. So then we have this SPcomp. This is a monad that combines probability and the option monad and a state all in one monad. Yeah, so computation can read and write to the heap, and it may fill. And it's this is a well-known monad construction. Then we work with the Kleisty category, and we have the usual composition here. We have the statistical distance between two functions, which is also the usual definition that I wanted to put it on the slide here, so you have access to it. And then some of the key properties is that this distance actually works by both. So if you have two functions that are small and you add a function on either the left or the right, then the distance will remain small. So that's makes it very easy to reason with. The nice thing here is that this it's not just regular category theory, but it's enriched category theory. So enriched category theory is where instead of usual category theory, you work with the HOM sets, but often it's the case that the sets actually have more structure. And here, so the structure is that of a quantile of positive real numbers plus and 0. And this is what's called a Lauvier metric space. So there's a very nice paper by Lauvier on showing that metric spaces can actually be very nicely captured by enriched categories. And that's precisely what we're using here. So we're developing all the sort of standard monadic programming or standard imperative programming in a functional language using monads. But then the extra addition is that we're doing enriched category theory, which allows us to keep track of all the bounds. This is implicit in SSProve and Rocq, and here we made it explicit. Although there is a two-categorical story in SSProve on the program logics that we haven't imported into Lean. So what I just wanted to get done was to actually have the smallest port of Lean of Rocq to Lean. So this is the monadic framework that I was talking about. So SSProve, it builds on Dijkstra monads. So Dijkstra monads give you a way of computing the weakest precondition, and the observation is that this is again a monadic structure, and you can do the weakest precondition on general monads. So it gives you a predicate transformer semantics on monadic computations. So this is a very general framework for organizing program logics, and we actually applied it with my co-authors in Rocq to state and probability, and there it works actually very nice. So the nice thing is that this well-developed Dijkstra monad framework, which was done to study the way that that F-star works, we could base it on the work by Kenji Millar in his thesis, then use that to develop a program logic for state and probability, and then you can just read off the read off the program logic. This has been ported to Lean, but in a simpler version in the what's it called, MCV Gen, and also in the Loom framework. They use the same setup, but they simplify it a bit, both because they use simpler programs, and because to verify some of the programs, you don't need all the coherence conditions. So it's strongly motivated by the Dijkstra monads, but they're not formalizing all the details. And then the relational Hoare logic, you can actually read off from the Dijkstra monad framework, and that gives you the couplings that are used in EasyCrypt also. And this gives us just a very powerful step-by-step reasoning. Here are some of the rules you will find, and those we will have those rules in EasyCrypt, and we derive them from a general framework in SSProve, and then and now we also have them in Lean. So we have the bind rule, sample, syncing, where we have one-sided sampling. We have deterministic steps and conditional case splits. And this can, for instance, be done showing that showing the security properties of a one-time pad. So that's the easiest example. Now, the other ingredient that was not in EasyCrypt yet, by now, that there's a paper that actually explains how to add it to EasyCrypt using the EasyCrypt module system. This is the state-separating proofs. It came out of the Everest projects, which had the aim. So this was Microsoft and INRIA with the aim of verifying TLS, and the way they developed. So this was an informal way of reasoning on a high level, and what we did in so that's an informal way in which cryptographers reason, but it was not connected to actual program logics. And we made that step in SSProve to connect this informal way of reasoning with packages to the program logic that we have in SSProve. So packages are stateful oracles with typed interfaces. So you have a bunch of inputs and a bunch of outputs, and you connect them. And then you can do parallel composition, just putting a program fragment after another, or you can do inlining of oracle calls or function calls if you want. So that's the linking. And then what's very important in the reasoning in state-separating proofs is the state separation. So if the program fragments only touch disjoint locations, then you have special reasoning rules. And the nice thing is you have the exchange rules known from monadal categories, and that's actually something that we make precise now in Lean, is that these packages actually form a monadal category, or an enriched monadal category, to be more precise. So the security proof is then a chain of package replacements. You can see something down here. For some reason, it falls a bit off my screen. Don't know precisely why that's happening. Then another aspect that was highlighted by some of our new collaborators, but they developed it independently by Marcus Krabbe and Carsten Schurman. So the way we had been developing packages was sort of like the Brown. So there's the well-known problem of names, formalizing names. And so we had been informal about it, and this actually led to all the usual problems when you're reasoning about names. And their observation was, well, you should just be using nominal sets, and that actually works very, very nicely. So what they so nominal sets, I mean, it's a tuples of sets with a G action on it. So you have a primitive operation of renaming, and that's precisely what you need to formalize syntax. And this has been very well developed in Isabelle, and so it's now also available in Rocq. There's a nice library for nominal sets, and I ported this to Lean also, and I'll make a pull request to make sure that this also becomes available in CSLib. There's some interest in it. And yeah, this should be useful in general for the Lean community. What I forgot to say, yeah, what I said, but what wasn't on the slide. So this is the work by Marcus Krabbe and Carsten Schurman, who actually showed that this nominal SSProve works very well and really reduces the proof size. So all the awkwardness that you usually have for reasoning about names, it's just gone. So if you look at the highlights from Rocq SSProve, there's the one-time pet, El Gamal, there's Snore, the zero knowledge proofs, there's the PRF, PRG, ChemDem, Sigma protocols. So many cryptographic protocols are already there. We're currently working on the KZG zero knowledge protocols. And it's the so it's I say here it's the first game-based crypto proofs, but of course there's Certicrypt that was before an FCF also. I think it's currently the only one that's maintained in Rocq. But what we do have, and we were the first to implement it, was this modular package algebra, which really helps you to do proofs nicely. Then the other thing that we have in SSProve Rocq is there's a cheeky reference to the Last Mile paper. Last Mile actually talks about the problem of connecting an implementation, a protocol verification to an actual implementation, and they make an important contribution there in EasyCrypt, getting that closer to the implementation. What we did was to narrow the gap even more, and the Jasmine compiler. Jasmine is a Rust-like assembly language, so it actually has some types and control flow, and then but it's still very low level, and it's extremely fast. But it allows you to control side channels. So that's the main contribution. And if you ever feel inclined to write Jasmine for assembly for security applications, have a look at Jasmine, because that's precisely what you want. So what we did there in the last yard paper is to bridge the abstract security proofs with executable implementations in assembly. So that's the gap between high-level games and low-level code. In porting SSProve to Lean, we did not port the Dijkstra monad framework. I'd like to still do that. So what we did in Rocq was we have the Dijkstra monads, and then we have the PRHL coupling, and then the statistical bounds. So in Lean, I wanted to go directly to the program logic, also because of the possibilities for tactics in Lean. That seemed like it might work. Also because the setup was slightly different, so I just wanted to see how far I could get. So and that turns out to work quite well. There's a downside. It's so the Lean tactics actually work better because they're directly working on Lean code and not some embedded code. The downside is that it's further away from what the cryptographers would write. So the code gets a bit shorter than what you would have in EasyCrypt, but it may be less readable for cryptographers. The nice thing is that just like in Rocq, there's a lot of stuff is already available in mathematical components. So here, what we're building on is MathLib in Lean. So we have the sub-probability distributions and the state probabilistic computation. So it's the combination of the previous monad with states, and then we have the usual operation, the usual monad operations. I just wanted to show you what this looks like in Lean, and then we can define the statistical distance. I had it on the slide before, but now this is in Lean in the extended real numbers. This is the same definition as we saw before. So this is the statistical difference between two functions, two computations, two Gleisli functions, if you want. And this gives us a pseudo metric. So we have that was it reflexivity and symmetry and a triangle inequality. And this is also something that I mentioned before. And both can quite easily be proved using coupling arguments from MathLib. And so this distance actually gives us the enrichment that I announced before. And now what we have is both the shallow embedding, where we directly encode, and this is closer to what FCF and VCV are doing. So to directly encode them as Lean functions. So this is something that we use for coupling, statistical bounds, and game hopping. And then we have the deep embedding, which gives us the code, and it's called raw code because later we quotient out by an equivalence relation. And this is very useful for package linking and structural transformations and so on. So we actually have access to both, and then we have an evaluation from the raw code into the probabilistic programs in Lean, and this actually gives us this is one way of obtaining the equivalence relation. So that's the evaluation here. What I've done is then looked at the tactics that EasyCrypt has, and there's a similar. There's a tool called Rocq that had a lot of tactics. So Rocq is an automation of the state separating proofs, which are also used in the GRF cryptography. And we looked at those tactics and we implemented them in Lean. And then we have we also looked at the tactics in EasyCrypt because there's a bit more automation in EasyCrypt, and also implemented them in SSProve. So I think we now have almost full coverage of what's available in EasyCrypt, also in SSProve-Lean. And the proofs become a bit shorter than the ones in EasyCrypt. Did I miss that's a good question? Not really. So the question is, did we move? And this is actually quite well known that the SMT proofs in EasyCrypt are not very well, not very maintainable. So what is useful is all the auto automation that we have in Lean, but we don't really need SMT. So with the regular automation in Lean, we can we can actually do most of the things that are done in EasyCrypt. Then there are these hybrid arguments, and there's a nice paper again by Marcus Krabbe and Carsten Schulman about how to do this in EasyCrypt. So that, or sorry, in SSProve. So this is a nice induction argument. This hybrid arguments comes from the initial state separating proofs paper, and they have a nice. So it has a nice implementation in SSProve in Rocq, and we ported that to Lean 2. And we formalized quite a few of the protocols they've done. We also managed to port them to Lean. And we also have the failure event lemma. So that's another thing we can port from another proof assistant. We have the nominal sets in Lean. That's also something that I mentioned before. And here's a quick overview of what we have. So we have the couplings. We have the computation is both direct and the free monad computation. We have a statistical distance, just like in EasyCrypt. We have a state primitive, and we have a deep embedding, free and so the free monad approach, and then the evaluation to the shallow embedding. And then finally, what I've ported was this. So we had a Rocq, or we have a Rocq interface from Hex. Hex is a tool for verification of Rust programs, and that both goes directly to Rust. There's now a project supported by the Ethereum Foundation to well, this has been completed, or I mean, the start of the backend is there. So that translates Rust to Lean, and we had it for the Rocq backend to Rust. We also targeted SSProve, and we automatically generated a proof that the functional and the imperative embedding agree, and we ported that to Lean too. So we can also have this SSProve in Lean can now also, in the same way as we had it for Hex, for Rocq and Hex, we have now ported it to Lean. So we can also do verification of Rust programs in Lean, or verification of high assurance Rust programs in Lean in this way. So you just to give you a short overview of what this looks like. We have the Rust implementation, then we extract Lean types and functions, then we go to the proof level abstraction, and then finally we define bridge theorems that bridge the Lean types with the encoding in the first encoding that we do into Rust. So this is the same as we would do it for Rocq. So just a quick comparison. So this is more. Oh, that's the last slide. I wanted to skip the comparison. So that's how far or what I wanted to present. I have a bit more, but that's something I want to check carefully before presenting it. So this is what I wanted to present. So how much I could translate from Rocq to Lean. And one thing I would be very interested in discussing, how this fits in the general Lean infrastructure. and some of the other projects that are going on in Lean to verify security, because there was no possibility to connect to SSProve before, and now I think we have the possibility to do that. So thank you.
Thank you. I'll quickly wait and see if anyone has immediate questions. Otherwise, I have a few as well.
I have one question. So you mentioned something negligible in the early part of the presentation, but the framework can deal with concrete level of security, correct? Like 1/228 stuff.
Yeah.
Okay.
Yeah. So it's all epsilon based.
I see.
Yeah. Just like in Rocq.
I see.
So I have one question. Could we have a quick look at some of the generated Lean code just to see what it looks like? So and part of that is I'm also curious basically how much of the translation was, fully automated. Did anything, how much cleanup was required? Did anything have to be kind of debugged by hand? If there's anything kind of interesting that wasn't possible to automate translation-wise, that would be quite interesting to see.
I'll release it. I don't want to search on my computer now and show you the gory details, but I'll make it available so we can look at it.
Yeah, that'd be great.
But it looks pretty okay, and it's as opposed to some of the other codes that's because we're porting from Rocq, a lot of the structure can just be can be copied from Rocq.
Yeah, and I suppose you're not trying to show equivalence between obviously the Lean implementation and the Rocq one either, right? Which makes things a bit simpler.
Yeah, that makes it So what I tried to do was to build a library in Rocq that has the same mathematical meaning as the one I built a library in Lean that has the same mathematical meaning as the one in Rocq, but they don't need to be equivalent in terms of type theory.
Yeah.
That would already be, difficult because this is another project that my PhD student Eske will present next week, I think, where we found out that the definitions of this in the standard library in Rocq and Lean, they differ in the recursion of, I think, the addition. So one starts by induction on the left hand and the other one on the right hand argument. So we were trying to compile Lean functions to Rocq functions and got very strange differences. And this was already because, the standard library is different. So I think the hope to prove this equivalence at scale will be very difficult if you actually get off the ground, if you actually do something that's depends on the standard library.
Yeah, so I think that part is quite interesting because then there's a question of, obviously, SSProve-Rocq is still in development, under active development. It's not intended, this translation to Lean isn't intended to deprecate it. And so I'm curious about kind of, what it would look like to try and obviously maintain SSProve-Lean in tandem with SSProve-Rocq and to feel like they're not, don't start diverging, or if they do start diverging, kind of how to handle that as a process or design goal or constraint.
I have a number of ideas about this. So far the porting went quite well because the original is quite well structured, and I have quite a bit of code by now. So once it has enough examples, it becomes easier to port. What I think would be really interesting is to have a joint blueprint. A blueprint is available for both Rocq and Lean, and to actually have a blueprint with pointers to Rocq and Lean. So we always have this intermediate layer that just clearly highlights what's meant. and then keep the blueprint in sync, and then hope that we can keep the code in sync separate from that.
Yeah, that could be quite interesting, especially if you never know if you get someone opens a PR to SSProve-Lean and then you have to translate it the other way.
Yeah.
That would be maybe that would be an interesting thing to test.
Yeah.
But yeah, I think the joint blueprint makes sense. Actually, that's quite a good idea.
Yeah. So at the moment, I mean, this was an experiment, but I know there are a number of people that would be really happy to collaborate on this. So I'll make sure I'll release this, so there's a possibility for other people to also work on it.
Yeah, we've had a lot of random first-time contributors pop up on our clip, so I think there, at least on the Lean side, there's people out there who will very plausibly open PRs and try to add things or try to add proofs or clean things up. But I'll let Derek ask his questions, or his hand has been raised for a bit of time.
Hey, boss. Thanks for the very interesting talk and work, as ever. So we've been using the hacks backend to try to just compile to get some cryptographic code into Lean, and have had some struggles, and there's fast progress being made on that. I wonder if, assuming the hacks backend were working perfectly for Lean, are there any impediments to, like, what are the impediments to using SSProve on production code now? I guess the SSProve in Lean.
I mean,
I guess the question is the bottleneck, which is hacks or SSProve-Lean, right?
Yeah, sorry, that was very poorly worded.
Yeah. So this is something that I developed quickly and certainly not ready for production. And I also don't produce production code. I mean, I do research. But I think that there's a very good possibility to turn this into, I mean, to verify. For instance, one of the things I would actually be close. I mean, that would be feasible, is to port the work that we did on TLS, to port that to Lean, and then also to port the. So we have the paper. It should be very easy to find online, where we verified TLS implementation in SSProve so with hacks, and then we used the libcrux primitives, and then we verified in SSProve that the cryptographic protocol was secure. We did the symbolic crypto using ProVerif, and then we did the panic freeness in FStar. And that proof can be ported to Lean. So those things are certainly possible.
Nice, really cool. Thanks.
Yeah, and it'd be quite interesting to see actually if there's any effect of some of the automation in Lean that isn't in Rocq. Like, I mean, grind obviously being one example. See if any of the proofs end up can be simplified, or if some kind of grind set can be developed and make the proofs a bit cleaner. That would be an interesting, an interesting example of porting it. Because I assume porting automation, because as much as the type series, you can find some kind of equivalence or relation between the underlying type series, then obviously tactics and automation, you kind of have to port. You're obviously not establishing maybe any equivalence between tactics, and it seems like obviously Lean is quite good for extensions of the language and the tactics and all of this. So maybe porting tactics from Lean to Rocq would actually be quite an interesting experiment.
Did you mean from Lean to Rocq or from Rocq to Lean?
Well, from Rocq to Lean feels easier because it feels like Lean is easier to extend in that sense. Like the metaprogramming is a bit better. And it would be interesting to see if you try to port tactics from Lean to Rocq, where maybe the experience in Rocq to add a new tactic or to develop it is like a bit rougher than it is in Lean. Obviously, I'm saying this without any hands-on experience of trying to do this. But it would be interesting to see if there was that could be one benefit of, something like grind in Rocq would be quite nice, for example.
Would be very nice. Yeah. I think that would be very interesting to try out. I don't know I actually brought it up on the Rocq Sulet before. So this is something that's very cool in Lean and that's missing in Rocq. The bits and pieces already, and it would be interesting to see whether it can be ported. I completely agree. The difference in meta language between Rocq and Lean is that so in Lean it seems to be a bit more convenient to use. In Rocq it's more verified.
Yeah, for sure. But yeah, that'd be interesting because obviously with Lean now and grind, like even in MassLib, there's a bit of a push to use grind increasingly much. And so that could mean that a lot of proofs become harder and harder to port back to Rocq, basically, if they increasingly depend on grind and there's no kind of equivalent. I mean, maybe there's some, there's a grind linter coming and maybe you can like pass the output of that and extract the kernel terms back to Rocq or something. But that would be something interesting, I think, with regards to kind of interoperability between proof assistants is suddenly if they start diverging in use of tactics and use of automation. I mean, same with Lean SMT. If you start having a lot of SMT-based proofs in Lean, maybe the support for that is different in Rocq and it becomes harder to port the proofs.
I did a small experiment porting from FStar, and there it seemed that grinds and the other Lean tactics are actually powerful enough, so you don't actually need SMT. There was one application where I found it that I really wanted to use it, and then I couldn't use it because the version was lacking. So I hope that can soon be upgraded. But mostly the standard automation in Lean is fast enough, so it's not entirely clear where you would need SMT actually.
Yep. Yeah. I think that's fair. But I mean, with grind, the big benefit is having access to grind sets, which makes it kind of very tweakable on a per project basis. I think grind is great, and we should be trying to use it more. I think we're hoping to just have every proof give you a grind for a lot of projects.
Just be grind,
basically. That's the future of proof readability. But yeah, that would definitely be like I think quite a fun project, and even reconstructing kind of proofs. I mean, kind of reconstructing even like human readable proofs out of grind would be like an interesting project, let alone porting it to translating these proofs to something in Rocq if there's no grind. I'll let Marco ask his questions.
Thanks for the talk. Just a question about I think they're called packages. So with the interface, is just that only a proof device, like to structure your proofs and your chain of equivalences, or can you actually use it for code structuring? Like you have a concrete module where you prove some properties inside, and then you're like. If your project is made of this module with these interfaces, then we know that some property is true.
Say again.
So the question is that just for proof structuring? So it has no practical use for like extraction or like connection with an implementation? Or can we use, like, if I have a project, so because you were mentioning the Everest project, so
that's a very good question. So it came from code structuring. In formal ideas about code structuring. What we did in the TLS work was actually my PhD student Lasse Hansen. He was verifying the TLS implementation in SSProve, and then found that some parts of the code didn't work well in the when extracted to packages. And then he had a deeper look and saw that it was actually nicer to re-export nicer to refactor the Rust code so that it fit nicer to the to the packages. So the packages also help you to structure the Rust code. There's no specific module structure, but it's a general categorical construction. I didn't present it, but it actually gives you a symmetric monodal category. I'm trying to write.
So the one question that I always had is when you you verify your individual pieces of code, like the primitives, maybe a little bit higher level than that, and then you have an interface where there is like where there could be an arbitrary number of calls. It seems like you get into this process calculate thing where you have this something a la prove-if. So you have different processes, they can call each other as many times as they want. There could be repetition. So you get into a sort of different proof model. It seems like you need to jump into prove-if or something like that. And I was wondering if it's using this these packages, you can prove some of the same properties or not.
I don't think it has been used in that way. So the packages have been discovered a number of times. So at least, I mean, it's one informal way of reasoning out of the Everest project, another way by Mike Roselick and his Joy of Cryptography. So and there it's a modular way of reasoning about imperative programs. So the more hardcore process calculus verification, I'm not sure it does that, although the process calculus was one of the motivations for SSP.
Okay, thanks.
Okay, so then if anyone has any last questions, I guess now is a good time to speak up, and then otherwise we're getting towards the hour, so we'll probably end it here for now, I think. But then maybe there'll be a future related talk about the new category flavored work in April or so, I believe.
Yeah.
Just one idea is that maybe it's interesting to develop some like Dolbear stuff, and then the soundness of symbolic model against the computational model on top of this work, and then the nominal sets will be useful in the symbolic world as well, I guess.
So that's a good suggestion. So there are a lot of several groups working on this. There is a computationally sound version of symbolic cryptography in Lean, but it's very restrictive. And there's also the CryptoVerif, which has a EasyCrypt backend. And I think that's another one, Bob D-Lean. I don't think that's let me finish my sentence first, and then I'll get to the question. There's a EasyCrypt backend for ProVerif, for CryptoVerif. So CryptoVerif is a symbolic checker for cryptography, which is sound in the computational model. And I think porting that to SSProve-Lean would be quite straightforward because we have many of the features from EasyCrypt. There's also Bob D-Lean. So that's a project which is a port of dy star to Lean, if I'm not mistaken. So that's a symbolic checker, and that's not known to be sound in the computational model. So that will be much harder. I did do a quick hack to try and see whether I could replay some of the symbolic proofs that we did in ProVerif in Lean, and that seemed hopeful. So I certainly think that this is feasible. It just hasn't been done yet.
Thank you.
Okay, that puts us right at the hour. So thanks to everyone who's stayed the whole time. Thanks to Baz, of course, for the great talk. And I think very interesting work that we don't see enough of, but hopefully we'll see more of this type of work in the future. And yeah, I'll stop the recording here. The talk will be online on YouTube later today. And then next week we have a talk from Baz's PhD student on more interoperability between proof assistants, but this time regarding verified compilers. And so hopefully see you all there. Thank you.
Thanks, everyone.
Sounds great. Thank you.